I am going to talk about fibroblast activating protein, which is quite a hot topic at the moment. Just the basics. I've been asked by my friends in Oman to present this lecture just to explain which molecules are currently interesting and what we are at the moment. So FAPi is expressed in malignant neoplasms of epithelial origin, and this is quite a high percentage of these cancers that expresses these activated fibroblasts as part of the pathological process. So this is a really good target for what we want to do. Resting fibroblasts are activated by epigenetic modulations, remodeling of the extracellular matrix, the secretion of certain factors, as well as oxidative stress. And then the fibroblasts are, of course, not the cancer cells themselves, but a immunoreactive cell that is deposited on the outside or in the extracellular matrix surrounding the tumor cells. This is really important when you start talking about therapy to realize that this receptor is not expressed on the cells themselves. In some instances, a little bit, but that's not the main way of expression. So it's really cells that envelope the tumor and the tumor cells. So if you apply these for therapy, you will be irradiating the tumor from outside the cells and not from the nucleus of the cell. There is different pan-tumor targeting agents. So when you talk about pan-tumor, we talk about one radiopharmaceutical that can target multiple cancers, regardless of the type of cancer or the original cancer. And this is really also important to know that these agents are a little bit less selective in some cases, like FAPi, for instance. So some of them still focus on cellular components, like integrin, CXCR4, FAPi, and so forth, while others are targeting processes like hypoxia, acidity, and then increased metabolism like FDG, as we all know. Then FAPi has autocrine and paracrine expression. I borrowed this picture from Perspective Therapeutics. It nicely says this. So traditionally, like if you look at PSMA or SSTR2, the expression is only on the cells themselves. As you can see here on the red. Whereas with FAPi, it is on the stroma, the cells surrounding the tumor, as well as sometimes on the cells themselves, although for me, still this is not the main mechanism. Mostly it's still FAP on the outside of the tumor cells. And as such, it's also important to remember that FAP is expressed in fibrosis, arthritis, and cancer and other diseases. So we are now currently at the clinical translation of FAPi. And if you look here where we were with PSMA, it took quite some years from target identification all the way up to therapeutic application. So please remember, we are still in the clinical translation phase. It's not yet that widespread used as a diagnostic tool, so we are still learning the constraints and the pitfalls and all of that of FOB imaging, but also for therapy, we still have a long way to go to optimize the therapy. And this is really the important message I want to give today. Just know what the constraints are when you do this kind of radiopharmaceutical. So, of course, in 2019, we had this beautiful image of the year, and this is where FOB really took off. And currently, the question still remains, in which indications is FAPi better than FDG, or is FDG better than FAPi, or you can use both? And the jury is still out. And if you look at different references, you get different answers. So I just kind of summarized here from 2 references how it looks at the moment, but comment down below if you have a different opinion or if you've seen a different reference to this, because this is really still under development and not very clear. But it seems that FAPi might be more appropriate in head and neck cancer of unknown primary, breast cancer, gastric cancer, pancreatic cancer, ovarian cancer, and so forth. FAPi is definitely less informative or proven less informative than FDG in hematologic neoplasms and thyroid and lung cancer. And then there is some instances where it's not clear which one is best. And here is just pictures to show you what differences the choice of FAPi versus FDG can make. So this is where I come in to tell you the different structures. So if you look at the MIP1232, that was the first FAPi targeting ligand ever investigated, but the choice was made to move over to quinoline derivatives. And so UMC was developed at Antwerp University in Belgium. And this was the core structure for further development of certain radiopharmaceuticals. Another group developed FAPi 04 and 02 without the double fluorine here. And the one is for iodine labeling, FAPi 01, and FAPi 02, of course, has the DOTA chelator for radiometal binding. So the guys from UAMC developed further into FAPi 46 and FAPi 34. So FAPi 46 is for gallium labeling and also maybe therapeutic, but this is not the most optimal molecule out there for that purposes. FAPi 34 is for technetium labeling, and FAPi 74 without the fluorine is for aluminium fluoride labeling with the NOTA chelator. So fluorine 18 is being made as pseudometal and then incorporated in the NOTA chelator. This was a very nice outline that I took from this article where they just explained the different components of FAPi. So as you see, the quinoline ring gives strong inhibition of FAP, but also provides selectivity over other similar enzymes. The double fluorine substitution increases affinity and selectivity, and most importantly, reduce the intracellular washout. And then you also get other patterns for FAP binding, and that is just optimized. So if we look at the pharmacokinetics, FAPi 02 and FAPi 04 was the starting examples. And as you can see, this is really important to remember with FAP radiopharmaceuticals that it accumulates nicely in the tumor, but it washes out as well. This is really important to remember because this is not influencing the diagnostic capabilities, but it is for sure going to influence the therapeutic efficacy. So if you use FAPi 02 or 4 for therapy, you will see washout of your tumors after a certain time. And if you match this with lutetium-177, for example, the radiopharmaceutical will wash out before it has reached therapeutic efficacy. FAPi 46 seems to be better in primary tumors, so it doesn't wash out after 3 hours at least, but it does seem to wash out of lymph nodes and distant metastases, so it's still not optimal. So FAPi 46 is still not optimal for therapy, but it's a really good diagnostic molecule, and it is currently the one used for gallium labeling. FAPi 74 here, same story, but it's really good for imaging. And here it's nice to see that they compared the gallium FAPi 74 with the aluminium fluoride FAPi 74, and you can see that they are equal. Well, they found them not to have a big difference. In FAPi 34, I just added here for completion. Labeling. So FAPi 46, normal gallium labeling, it's quite the same as your dotatate or your PSMA labeling. Very important that there is a possibility of radiolysis. You have to add additional ascorbic acid. This figures comes courtesy of Stellenbosch University, South Africa, where they validated the FAPi tracer. And they found also that, importantly, it's not visible on ITLC that radiolysis has occurred. So you have to do HPLC analysis. Unfortunately, you have to, especially during validation, because these guys are not the FAPi you are looking for. So they will distribute differently and influence the quality of your scans. And this yielded after 2 hours a radiopharmaceutical with only a 91% purity. So please do HPLC during validation, watch out for radiolysis with these molecules, and make sure that you make a pure radiopharmaceutical. I also found similar reports in literature where they added these different radiolysis protectors. And as you can see, there is definitely optimization to be done. We found ascorbic acid to be good in higher amounts. So I'm just adding here the method that I am validating at the moment with 100 microliters of ascorbate buffer already inside the radio labeling mixture, and then 900 microliters of the ascorbate buffer in the end to buffer protect the final formulation. So please have a look at this when you validate. Then FAPi 74 we do here in Belgium at EZ Lever. So this is making the fluorine pseudometal aluminum fluoride and labeling it. And then also this is a beautiful method. It's also developed by Sophie Biosciences. So it is available through commercial partnership, and it works also really good with high yields. Then there is technetium, working with the isolink system. It was published here for preclinical. Not sure if this will go into the clinic soon or if it's already being used. Also not sure about the claim for rhenium therapy for this guy, because this needs to be optimized for sure. It's not just a statement that if it works for technetium, it will work for rhenium. This is proven not true. As yet, I have had to see a rhenium labeled FAPi. And of course, the question gallium-68 or fluorine-18 is merely about logistics and what is available in your facility. So there is no scientific reason for the choice between the two, it seems at the moment. So now we go to the therapeutic application of FAPi, because this is what everybody is excited about. And as you can see, this is an example of lutetium PSMA, where after 96 hours, you still have activity in the lesions you need. And this is really important to make sure that your radiopharmaceutical stays this long in the area of interest. So the molecules need optimization. So firstly, there is the drive to design other FAP targeting vectors that is not maybe based on this pharmacophore of the FAPi 04. There is also multimerization strategies that seems quite interesting, where you have 2 FAPi molecules for every radiopharmaceutical, and then also albumin binding is being investigated. So FAPi 2286 seems to be quite good. I don't know, did I write it here? This is the lutetium FAPi 2286, where it has a longer tumor retention. They demonstrated kind of up to 10 days, but there is a mixed response. And this is still under investigation. But FAPi 2286 seems to be a bit more optimal with regards to tumor washout. Then the multimerization strategy, where you have your chelator, and then one FAPi molecule and another FAPi molecule, is also very strongly investigated and also evaluated over a long time. And definitely this also results in higher tumor retention. So this is also a valid strategy to pursue. And then you also have these guys looking at albumin binding fragments, where you have your chelator, your FAPi, and then a molecule that binds to albumin in the blood and increases blood retention and hopefully tumor accumulation. But as we can see, and this is quite telling, is that every year another FAPi is being tested in some patients for FAPi therapy. So we definitely don't have the most optimal FAPi yet. It's mostly Germany and some other non-European countries that are testing this due to the regulation constraints in some countries. But you can see also that there is no consensus on which radionuclide would be best for this application. Now, from what I hear is that definitely a beta minus emitter seems to be more appropriate, because as we discussed, the radionuclide and the FAPi is not incorporated into the tumor cells per se, but rather on the other cells surrounding the tumor. So you want something with a longer range that will do damage throughout the tumor. So definitely there is still a lot of optimization. So it's just clear from this picture that over the last 6 years, we have been trying multiple FAPis, we've been trying multiple radionuclides, we have been trying multiple diseases, and we have been trying multiple radioactive doses, all in small cohorts. So currently, we don't know what is best therapy yet. So I really want to stress that. Here I have a picture just about how easy it is to label. So, of course, please keep in mind, it's really easy. You can take your FAPi04 and label it with lutetium or actinium. That is not the problem. The problem is what patients to select, what FAPi to take, what radionuclide to take, and what dosage to take. So all of this is still under research, and it's by far not ready for clinical application on a widespread use yet. Should you want to endeavor into therapy, no, you are delving into the research realm. So there is well-established options for imaging. FAPi 46 and 74 seems most advanced, but the other FAPis are also suitable for diagnostic, and therapeutic FAPi molecules are still under development. So it's a nice journey that we are all on, and I'm really excited about the future. And yeah, I will possibly make update videos on this. Please put your comments down below and tell me what you think about my opinions, and thank you for listening.